So are we ready, more or less?
Hang on, give me 1 second to start the live stream on YouTube.
Okay.
Okay, it started.
Oh boy. Well, welcome to yet another meeting of the Los Angeles Astronomical Society. Evidently, the email did not include the link, so we have a relatively small number of people on Zoom. And of course, our door prize ticket guy did not show up for those people who are here. I don't really know what to do about door prizes, but we'll think of something, or maybe we'll skip them this meeting and double them next meeting, and that will convince people to show up. As you can tell by looking at me, I am not Daryl. I have done this job before once or twice, and Daryl sent an email message that he was not well and really should not be here, giving his disease to everyone else. And when I came in the room today, all fingers pointed at me, and I wind up standing here in front of you today. The first thing I want to do is what I always do, what we always do, and that is to ask if there are any new members here in the house. And I see 1, 2, back in the corner. So tell us who you are. Ah, okay. Need another mic or this one?
Here, why don't we do this? You speak into this one, and I'll pass the mic around. Okay. See that? Cool. So we'll do unmute here. There you go. That one's live.
Oh boy.
You just clip that on.
Okay.
Yeah. So if you guys want to ask questions while on Zoom, while this is going on, if you don't speak into the microphone, Zoom can't hear you. So, if you have a question, we'll pass the microphone around.
And I'll speak into this one. Oh boy.
Thank you. My name is Bill, and I've been a member for several years, but this is my first meeting I've actually rearranged my priorities so I could actually get here. I've been interested in astronomy since I was a tot, but I've never had a telescope, and I still don't, so I feel like hiding, but at least I'm here.
Yeah. You don't need a telescope to be $20.
We have plenty of scopes for you to borrow.
Oh boy, thank you. And we had another new member up there. Okay.
Are you a member yet? I don't know. She's a guest for sure.
Hi guys, my name is Melissa, and I'm like a month new, I guess. Yeah, I just love the stars, and I do have a telescope, a refractor, and I have like a little equatorial mount, and then I also do photos with my camera that I can do of like Milky Way stuff and Joshua Tree and Malibu last night, late at night kind of stuff. So yeah, I'm happy to be here and happy to meet everybody.
Oh boy. Are there any other new members or guests here? How about on Zoom? I can't see or hear anything from Zoom. I think Evan will go fix that.
Yeah, I'm gonna be able to run around like that.
I've been asked
new members on
to
Zoom?
announce even to the small number of people here that if you left anything at the Steve Kufeld Astronomical site in Lockwood Valley, go get it because Keith is going to throw it in the dumpster. So you've been warned.
I think we might have 1 or 2 new members on Zoom.
Aha. Have them speak up.
Or maybe not.
Okay. Well, is there anything else critically important to announce?
Yes, the 28th.
Oh, yes, of course. Halloween Science Night at Garvey Ranch Observatory on Saturday, October 28th. Everybody to be there. If you're not, we're going to revoke your membership and fine you and do all kinds. Okay, maybe not, but Saturday, October 20th. running until 9 p.m. or something like that. It's a Halloween event. Bring your kids, lots of candy, lots of fun. Scary people like me dressed up in my wizard's costume to answer questions. Well, lots of science stuff there, making comments, talking about the universe. It's the great place to be. It's those of you who are used to it, Giovanni Somoza, sorry about that, Gio, always runs it for us, and he does a really great job. So is there anything else I forgot? Well, in that case, let's bring on our speaker. Once we get his picture up here. Aha, I see him. So, evening, there he is, staring intently at the computer. Marco Velli has joined appointments to UCLA and JPL, and he is on the science team for the Parker Solar Probe, which, unlike some other ships, actually is going where no one and no ship and no thing has ever gone before. People keep telling, why don't we drop all the radioactive waste or stuff? And they say, well, we're dropping spacecraft in, well, not quite into the sun, but pretty close to into the sun. And Marco is going to tell us all about it. And I'm going to tell him, go ahead and take it away, and somebody's going to teach me how to mute this dang thing. Okay?
How much time do I have to speak?
Uh,
What time do you want me to take? Half hour, 45 minutes?
yeah, you've got about an hour. That ought to do.
Okay, I
So you
just
can
want to know how far and how much of an introduction you wanted. And well, let me start. And I'll try to make the introduction probably fast. Let me share my screen here. Tell me if you see my screen. And then I'll play my slideshow.
Yeah, we see your screen,
Okay. Sounds good.
and we see your slideshow. Thank you.
Okay. All right. So thanks for having me. It's great to talk to you. I've spoken once before at Griffith. I'm sorry I'm not there in person. I thought I might make it, but in the end I couldn't. So I'm Marco Velli, and I teach space physics over at UCLA. But for a long time I was at JPL, and one of the primary things that I was doing at JPL was trying to push for the flight of a solar probe. So I'm going to give you a little bit of interest of history, because solar probes history is intimately connected with basically the birth of the space age, and everything about the heliosphere is connected to the early space age. So let me just go very quickly and explain what I'm going to talk about. So I'm going to start before the space age, then we're going to go to solar wind and what we knew about the heliosphere before Parker Solar Probe and solar orbiter. I won't mention solar orbiter as much, but I'll say a few things about that. Let me see if I can get a laser pen here going. So that might work. Let's make it blue maybe. And oh no, laser pointer has got to be red. Okay, it doesn't matter. Then I'll talk about solar wind, and then what Parker Solar Probe and what its novelty is, and some observations and how it's changed our view of the heliosphere, because that's really happened. And I'll define what the heliosphere is in a second. You're going to see it pictorially here. So I like to start out with Douglas Adams' famous statement at the beginning of his Hitchhiker's Guide: far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies an unregarded yellow sun. And of course, that makes comedy, but it's everything but true, because the sun has always been very, very heavily regarded. But anyway, let's take a look at the sun. The sun is, as you probably know better than I do, because most amateur astronomers know a lot more than us fellows. Although I am an amateur astronomer as well, so that kind of helps me. Is a small. It's what's called a G2 subdwarf. It's a smallish star, but at least it lives long enough to have people like us on it or close to it. And it sits in the interstellar medium, in which it's moving at about 100 kilometers per second. And it's actually in a very interesting place where there's a lot of stuff going on in the interstellar medium. And of course, there's a lot of cosmic rays out there. And we know about how far the influence of the sun and how it protects us from cosmic ray is, because we've sent out 2 spacecraft. In fact, JPL sent out 2 spacecraft in the 70s, the Voyager spacecraft, that have managed to go all the way out to the shock that separates the solar wind that I'll tell you about from the part which merges with the interstellar wind. And in fact, they've gone beyond that. And we now know that there is probably not a bow shock in front of the heliosphere, even though it's going supersonic, there's mass loading. And so in fact, the transition appears to have not a shock, but we've gone well beyond the termination shock of our own solar wind at about 100 astronomical units away. Voyager 1 slightly north, Voyager 2 slightly south, and they're both still sending signals. So it's very successful from the 70s. So we've been all the way out there, and there are plans to go further away. But tonight's talk is about why does this bubble drawn like this, even though it's an incorrect shape, assuming that it's spherical, why does this bubble even exist? And you know, how did we determine that? So I don't know how much you know about the sun. Just give me some numbers here. The sun-Earth distance is about 150 million kilometers. In solar radii, that's about 215 solar radii. The radius of the sun is 700,000 kilometers. And the sun is, you know, when you cut it down to like something like an orange, it's got a core where the nuclear fusion reactions are occurring. And then it has what's called a radiative zone extending about 2/3 of the radius, and then it goes convective. And when it goes convective, that's where the magic kind of happens, and you get a magnetic field which is formed. You reach the visible surface, the stuff that you were watching during the annular eclipse today, which is not a surface at all, really. It's really just a region defined by optical properties. It's just that the sun doesn't end there, but the sun above the photosphere is transparent to radiation. And so you see the last surface, just like the surface of a cloud, and that's the photosphere. And that sits at about 5,500 degrees Kelvin. That's something in the range of 10,000, 11,000 degrees Fahrenheit. But some weird stuff happens further out where the solar corona is, which you see during total solar eclipses. And I'll show you a picture from the last great American solar eclipse right away. So this is what you see when the moon manages to block out the sun completely, and you see structure. And that's kind of amazing, right? Because on the sun, you really see a spherical ball, but when you look at the corona, it's got a weird shape. And your eye sees something much more similar to this picture than what the cell phone manages to take because of the brightness of the corona. But your eye sees structure, and there's tons of structure, and there's things floating in the corona. You see these little red things here that are called prominences. They're pieces of an outer layer above the photosphere called the chromosphere. And you might wonder, you know, why does this thing exist? And this exists, and the existence of this, of course, is intrinsically related to the presence of a magnetic field. But when did we learn that the sun is a magnetic star? Well, a person very important for the history of astronomy in general, and in particular in Southern California, George Ellery Hale, is the person that invented the instrument to look at the photosphere and measure the Zeeman effect. And the minute he used the spectroheliograph to look at the sun, he confirmed that sunspots were magnetic. So basically in the 20s, actually earlier, it was closer to 1907, 1908, but his last paper, his most important paper, is published in 1919 Astrophysical Journal, in which he found that, you know, the sunspots are a magnetic process. Now, before that, but already in scientific times, that there was some activity going on the sun had been observed by an astronomer, a British astronomer, Carrington, who unfortunately had to stop making his observations at some point to go back and work at his dad's brewery. Anyway, Carrington observed what's called a white light solar flare, which is a brightening in white light of a certain region of the photosphere. And it comes from regions around sunspot, and noticed that intense auroras occurred 16 hours later. That led to a whole theory of the connection between stuff that was going on in the sun and at the Earth. And Fitzgerald and Lodge in the 1890s proposed that there were clouds of charged particles coming from the sun and hitting the Earth, traveling at fairly high speeds, 480 kilometers per second. Now, take into account that we didn't know what the temperature of the solar corona was. 480 kilometers per second, to all intents and purposes, is an incredibly supersonic flow. But of course, the principle of authority in science always holds. Lord Kelvin said it was a coincidence, and that kind of stopped studies in the UK in their tracks. And I haven't traced what happened in Norway, of course, where studies kept going because they were sitting under the aurora most of the time. And so Birkeland made experiments and things like that. But a better model was created in the UK by Chapman and Ferraro, in which they proposed that, once in a while, these particles could come from the sun and they would compress the Earth's magnetosphere, leading to what we call now geomagnetic storms and substorms. Now, in the 1860s, Young had observed some weird lines, emission lines in the solar corona, and he called them, attributed them to an atom called coronium. But it was realized in the 30s and 40s by Grotrin and independently Edlin that these were actually highly ionized iron ionized 13 times. And that means that the temperature, the electrons sitting up there in that gas, had to have a temperature of above 1 million degrees. And that's where, real mystery occurred, because now all of a sudden we know that the photosphere from our observations is at 6,000 degrees Kelvin, 5,500, whatever. And then the corona, which is further away from the nuclear fusion source, is sitting at 1 million degrees. And so that generated a huge problem, which is, why does the sun have a corona at all? Now, once you know that this is a gas at 1 million degrees, you start understanding why this is structure. The structure is there because that means that essentially hydrogen is completely ionized. And therefore, if you have magnetic fields constrain the motion of particles that we will say in a second. And that leads to these beautiful structures that you see in the solar corona. But it took a while before the consequences of this were understood. Biermann in the 50s was looking at comet tails, and you amateur astronomers have seen this also. They know that comet tails are typically bifurcated. They're not one simple tail. Well, there's one tail that follows the orbit and the effects of radiation pressure and the orbit itself, which is this whitish tail that you see here, or this curved tail that you see here. But there's another tail which appears with a slightly colored hinge. It goes straight radially away from the sun. And Biermann thought there must be particles coming from the sun that sort of interact with the ions that are generated by radiation hitting the comet and dragging them away. And from the shape of these comet tails, he estimated it was 470 kilometers per second. Now, Biermann happened to be in those years at Chicago, where Gene Parker was a young researcher. And so Gene Parker started thinking about this problem. People understood that if a 1 million degree gas would have an extended atmosphere, and somehow this gas should be all the way, there should be some density all the way to the Earth. Some Chapman and Chamberlain had made models of this. But that was kind of weird with respect to what we knew. So on the left here, I'm just showing you a very, very up-to-date from 1947, end of Second World War, image of what we thought happened as you moved away from the Earth. And it was well known since Marconi, of course, that you had an ionosphere. You would reflect on the ions, you'd reflect electromagnetic waves, short waves of various, and that defines various regions. But if you look at the temperature, it was well known the temperature drops, and everyone who's flown on an airplane knows that the temperature is in the minus 40s, minus 50s at 10,000 meters, 33,000 feet. But then the temperature was observed by rockets, and you notice this is the V2, what would essentially become the Explorer kind of rocket once von Braun had come to the United States. The temperature started going up. And here's now asking the question, how far up does the temperature go? There's a question mark. And then here, this outreach person assumed that there was a void between the Earth and the Moon, about minus 273 degrees. So anyway, in 1957, the space age is born, as you can see here from the title of page of the New York Times. Completely unexpected not only to the US, although they knew that the Russians were very quickly trying to, but the US was plagued by the fact that there was competition between the Navy, the Air Force, and the Army, well, more the Navy and the Air Force, in trying to develop a rocket. And so the Sputnik launch triggered all sorts of things. But the New York Times published an interesting article that you can go and read if you want, but it basically went into full protection mode. It was trying to convince people not to be afraid of this, and that, we couldn't really use satellites to drop bombs or to spy. The only thing that we could use them for was a program of research, understanding the nature of the sun, cosmic radiation, solar radio interference, and all of this. And of course, that this would be required and necessary for sending missiles and eventually man into the vast reaches of the solar system. So basically in 57, the New York Times predicts what we now have as a space program, the part that has to do with space weather and situational awareness, and the fact that we need to understand what on Earth is going on at the sun. Be that as it may, soon after that, Gene Parker publishes his paper, seminal paper, Dynamics of Interplanetary Gas and Magnetic Fields. And he says, guys, if you have a gas at 2 million degrees in the sun, right at the sun, that there is no way that's going to remain static. The interstellar medium basically has zero pressure. That means this gas is going to accelerate. It's going to go into the interstellar medium, and probably hit a shock or something. But anyway, you're going to have a supersonic outflow. And so the Earth should be immersed in a supersonic outflow. And that's a photo of myself discussing with Parker. He was still alive at the launch of Parker Solar Probe. In fact, one of my PhD students wrote his final science paper with Gene. And so we had a lot of interesting conversations. I became good friends with him. Unfortunately, he passed away. Now it's been a year and a half, almost 2 years ago. In any case, that prediction, 1958, came right at the birth of the space age. And in fact, the same year, NASA was born with the Space Act. And that by October 1958, the Simpson Committee said that, what we're going to do when we go to space. Well, there's a series of committees was put together as to what to do once we would get rockets that would go into space. And Simpson was responsible for the Particle and Fields Committee. And he said, well, one of the most important things is to have a solar probe that goes inside the orbit of Mercury to study what's going on really close to the sun. Now, the first measurements in situ of what was going on were made by mistake by another of Korolev's projects, which was the Luna projects, the Luna 1 and Luna 2, that he called Mechta as a diminutive. And basically, the launch of Luna 1 was successful, but Luna 1 missed the moon. Now we have computers, your cell phones have more calculating power than the best computers that we used to land on the moon in the 60s, but it's a difficult thing to do. And Mechta missed the moon, and it was the first man-made satellite in the solar system. And it had a particles detector, and it measured a few intermittently, but it measured a very fast outflow coming from the sun. But the continuous, then of course, I'm not mentioning, of course, the fact that we had Explorer 1 in 58, and we had the beginning of the discovery of the Van Allen belts and the beginning of the American space program. But we have here Marcia Neugebauer at the NASA press conference in 1962 from Mariner 2 going to Venus, which could measure particles and fields continuously. And here we have the original data, the measurement of the speed of the solar wind as a function of distance. Set 0.77 is the orbit of Mercury, and you can see that there's a flow. In fact, you can see that it's a variable outflow, minimum speed slightly below 400 kilometers per second, maximum speeds all the way up to 800. And that's Marcia Neugebauer there, and that's Marcia today. And Ed Smith was a member of some of these early experiments for magnetic fields. And they are both colleagues at JPL. Marcia and Smith unfortunately passed away a few years ago now. Marcia is still alive and well and came to the last solar wind meeting. So again, to summarize, life on Earth comes from the radiation of the sun's photosphere, and that's the famous 1.36 kilowatt per square meter at the Earth. But really, the supersonic solar wind that drags out this hot corona into it's only a few thousandths of a percent of the intensity of sun radiation. But it's really important because it's magnetized, and magnetic fields can focus energy and then release it in bursts. And so that gives rise to all the space weather effects. On the positive side, it protects us from galactic cosmic rays. So an active sun is dangerous because if you have a flare, it will hurt an astronaut, but it protects us from galactic cosmic rays. And the heliosphere is what we discussed, is this bubble created by the solar wind and the interplanetary medium. Now, we know from before Solar Probe that the heliosphere breathes with solar magnetic activity. So this is a polar plot of the solar wind speed as a function of latitude carried out by the Ulysses spacecraft, another JPL mission, in conjunction with ESA, European Space Agency, which was flying in the 90s and early 2000s. What you see here is a polar plot of the wind speed as a function of latitude. So we sit in the ecliptic plane and we see kind of jetting between fast and slow, much like you saw in that diagram for Mariner when it went to Venus, higher speeds and lower speeds, higher speeds and lower speeds. But once you get up about 30 degrees latitude, the solar wind kind of settles into a very, very high speed solar wind at solar minimum, when you don't have many sunspots, solar minimum right down here. And there's clearly some turbulence involved here. There's a variability between 800 and 720 kilometers per second. But then around the equator, you have kind of a very strange, where the streamers are, you have this kind of intermittent flow. At solar maximum, anything goes. You have a mix between wind at 900 kilometers per second and very slow solar wind at all latitudes. When you revert to solar minimum, then this was the very deep solar minimum of about 12 years ago, 15 years ago now, actually, where you see this wind speed is now the polarity, the red and blue is the polarity of the magnetic field. So At this solar minimum, we had an outward field in the north, an inward field at the south, and then at the last solar minimum, it was reversed. So this shows that, during the solar activity cycle in 11 years, the magnetic field actually inverts. And this is an in situ demonstration that must be the case. And so we now know something about the structure. These are measurements that occur between 1.3 astronomical units. Ulysses never came closer to the sun than the Earth is, but it went all the way out to Jupiter. That's how it got its kick to get out of the heliosphere. Now, 1 million degrees means that it's a plasma, as I was telling you. So let me explain a little bit, first of all, why there's a solar wind, to those of you. So very simply, if you take if you have a 1 million degree gas in which you've removed the electrons from the protons, the thermal speed of the electrons and protons is very different, because that speed corresponds to more or less the same temperature. That means that, at about 1 million degrees to 1 million degrees, protons move at about 100 kilometers per second. That's much lower than the escape speed from the sun, which is around 600 kilometers per second. On the other hand, electrons, which are moving essentially 42 times faster, 41.4 sometimes faster, they're going above 4,000 kilometers per second. So they don't feel gravity anymore. They feel free to go. So they take off. But that sets up, you can't charge the sun, right? So that sets up an electric field that drags out the protons and pushes back the electrons until the sun doesn't charge and there's no net current outflowing from the sun. And that's really the source of the solar wind from the point of view of the just the general physicist. Now, there's some further stuff going on, though, and a plasma is different from neutral particles, because in a plasma, when these charged particles collide, the number of collisions decrease as the temperature goes up. If you think of yourselves in a theater, trying to get to the exit at the end of a movie, and you increase your speed and you're moving randomly, the number of collision goes up. Because if the cross-section of people is the same, the number of collisions increases with the speed you have. But in a plasma, what happens is that particles look smaller if you're moving faster. And so you have less collisions as your speed increases. And for one, that means that as the temperature goes up, a hotter and hotter plasma, if you have some external force or some source of energy, that energy will preferentially go to the particles that are already faster. That's one of the reasons we have cosmic rays. That's point one. Point two is that charged particles have to follow magnetic field lines. They gyrate around them. Basically, they move around the magnetic field. They can go very fast along the field, but they can't really go across that field very well. Well, it depends whether the particles or the fields win. If there's more particles, more gas than fields, then the particles can actually drag the magnetic field with them. But to lowest order, they must follow each other. So you can think of a plasma as being kind of a fluid-like thing where the magnetic field provides the fluid behavior of it. So magnetic field lines must follow charged particles. And so you get this self-consistent molasses. It's not really molasses because it's highly conductive, but it's a self-consistent thing that provides structure and confinement. What I like to tell people that are not involved in plasma physics is that particles and fields are inextricably intertwined. And if you repeat that to yourself 10 times, you must get the idea of what it means to be a plasma in a magnetic field. And so there are processes that occur, and believe it or not, at the same time is when nuclear fusion had been basically discovered in bombs. That's in the early 50s. And then we attempted to create nuclear fusion machines, and that was a secret program in the US. It was called Project Sherwood. But then by the end of the 50s, the Russians realized that we were very far from it. They went public. They started arguing about the instabilities that they saw. And some of these processes are called magnetic reconnection and loss of confinement. And these processes are fundamental in what happens in space and in the solar corona. So I'm just reminding you that all this happened at the same time as the birth of the space age. So what do you mean by dragging out of the magnetic field? So imagine the sun to have basically a dipole magnetic field. When you allow for the gas to escape, what happens is it drags the field lines open. And then if you take into account the fact that the sun is also rotating, it twists these field lines up. So this is when you're measuring something in situ in the solar wind, you see this twisted rotating magnetic field if you're up here. Close to the equator, you have some closed field lines. It does provide some confinement, but there's a lot of instability problems, and you're going to see that in movies from Parker Solar Probe. Take it that also the magnetic axis of the sun and its rotational axis don't coincide. By the way, the sun's rotation axis is inclined 7 degrees from the ecliptic plane, as was first measured by a Jesuit priest who was fighting with Galileo, Scheiner. And you also see that because of that, the equator, if you have open field lines on one side of one sign and open field lines on the opposite side on the other side, that means that you have a current circulating around the sun, which is called the heliospheric current sheet. And that current sheet, because of this inclination, gets warped into what has been called previously the ballerina's curve. So the Earth in its orbit moves between the southern and northern parts, and so it observes the magnetic field continuously oscillating, and probe will do that as well. Anyway, what I told you, you would think that the source of the solar wind has to do with electrons being able to escape. That means that if you heat the electrons even more, you would expect a faster wind. Oh, wait a minute, Ulysses showed that that's not quite true. There's an indirect way to measure the temperature of electrons and the speed of the wind at the same time. And what Ulysses showed that in fact, the highest speed solar wind came from the coldest regions on the sun, the so-called coronal holes. While the slowest solar wind, the speed here is on the left-hand side, it's kilometers per second, came from the hottest regions on the sun. And that probably is a magnetic effect, where the closed magnetic arches occur, where coronal heating is more effective and you have equilibrium between protons and electrons. Well, in the coronal hole, the proton temperature seems to be very high, but the electrons scarcely reach 1,000,000 degrees. So that's one of the mysteries that probe was going to try to explore. The coronal heating problem is really a problem of work, right? Because you cannot thermodynamically bring energy from a cold region to a hot region. So the photosphere cannot heat the corona thermodynamically because it's colder, and heat does not naturally flow from something cold to something hot. So that means that there's something that must be, we're doing work. Again, who can do work? That's the magnetic field. So the magnetic field emerging from the sun can shake and twist around with waves and produce currents up in the corona that can dissipate. And forget the equations, they're not for you, but this is a temperature profile. So we think that there's a flux of electromagnetic energy generated by inside the sun, the dynamo, that then allows the corona to become hot and to expand and to become turbulent. And in fact, in the solar wind, where the plasma is really kinetic, it doesn't have any fluid behavior at all, you get incredible distribution functions with accelerated particles and so on. So let me skip that. So in addition to Solar Probe that was launched in 2018, we've launched a mission called Solar Orbiter that has telescopes that goes to the orbit of Venus. And this is really showing you the electrodynamics of the corona in very, very fine detail. If you look at it, you see that there's all these small arches. Now you're not seeing the magnetic field, you can only see the plasma. And this is sensitive to lines that are hundreds of thousands of degrees. So we're looking at plasma at hundreds of thousands of degrees outside the photosphere, which appears dark in this wavelength. But you see that at very small scales, you have all these small little brightenings. And these have to do with the storage and release of magnetic energy. So let's get to Solar Probe. Solar Probe was thought up as a JPL mission in the 70s. We wanted to go close to the sun to understand precisely what's going on. How is the corona heated? How is the wind accelerated? How do you create solar energetic particles? And also to test general relativity. And the idea was to send a probe out to Jupiter, kick it into a polar orbit, and come crashing down. At the time, we thought that the solar wind became supersonic at around 5 solar radii. So the idea was to go inside 5 solar radii to 4 solar radii where the wind was subsonic, and to do that. So this is Star Probe. Then the mission continued on the mission until the late 80s with this kind of conical cross section. I was involved in the last iterations of Solar Probe, in which we were still trying to go to 4 solar radii. This was no longer at JPL now, it was at the Applied Physics Lab at Johns Hopkins in Baltimore. And then we realized that we didn't have the technology to do this mission, because on the one hand, we didn't have solar panels that could at the same time push us all the way out to Jupiter and then allow us to use energy really close to the sun, 4 solar radii. And we did not have nuclear powered engines or thermal nuclear power like Voyager had or like Ulysses had, which would allow us to get to Jupiter. They're no longer in use for civil spacecraft. So we had to use solar panels. And so the mission completely radically changed. We studied new orbits, and we decided that instead of going all the way out to Jupiter, we would remain in the ecliptic plane. The other important thing that I forget that I'm waiting to mention is that in a mission like this, the time that it takes from going pole to pole is only 16 hours. So imagine now spending $1.5 billion for a 16-hour mission, pole to pole. That would have been really, just calibrating the data would have taken so much. So we opted for a mission that stays in the ecliptic plane and uses Venus gravity assists, multiple Venus gravity assists, to work its way closer and closer to the sun. And the idea is not to get down to 4 solar radii, but to get inside the region where the magnetic field still shapes the wind, where the speed of the wind is smaller than the typical magnetic speed, which is called the Alfvén speed. And so we think that's about 12 solar radii. And so Solar Probe is pushing to go into about 9.8 solar radii from center, 8.8 from the solar surface. It used to be called Solar Probe Plus. It was named in honor of Gene Parker, who was 90, because we were really trying to get at the heart of the origin of the solar corona. Okay, Solar Orbiter is a very similar mission that was launched a little bit later. One more thing that is really important to know is that the solar wind is turbulent. In fact, the solar wind is one of the cleanest example of turbulence in nature. And you can see these beautiful power law spectra if you're familiar with turbulence. The energy as a function of frequency obeys a power law. And there was a prediction from a very famous Russian mathematician called Mogorov that it should be 5/3. And it really looks like that. But we need to understand what the origin of this turbulence is. So what does probe look like? It has a thermal shield. It's no longer a cone. It's just a flat shield. It has 4 electromagnetic field antennae sitting at the front of the spacecraft, so they measure the pristine solar wind and not the noisy wake of the spacecraft. It has a Faraday cup to measure very fast particles outside, peaking outside the shield. The shield reaches temperatures above 2000 degrees Fahrenheit, 1200 degrees centigrade. But behind it, there's a radiator that you see here, and the radiator is made with water. It's the highest capacity, most simple compound that we have and that we could recognize if something happened. Behind that are solar panels that bend in and get partially occulted as you move closer to the sun. And then on the boom, we have the magnetometers. Using the shield as an occulter, we have a white light telescope called WHISPER. And sitting in the back, we have high energy particle instruments and then other particle instruments that use aberration to measure the distribution functions observed. So this is the launch of Parker. Maybe there's a question in the chat.
Minus 15. Roll for ignition.
Okay, right. Yeah. So this is just
10, 9.
so this was
8,
August 12th, 2018, 5 years ago.
6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the sun.
Yeah, let me stop there. And so where are we? Basically, we've now gone through, as you can see, our first 3 perihelia were at 35 solar radii. Then we went down to 33, then we down to 30, then to 20. And we now had our first perihelion at 11 solar radii. So we see we're more than midway. And the global mission has 7 Venus encounters to knock us closer, and we're missing 1. So now we're going to have 5 perihelia at 11 solar radii, and then we're going to have the final 3 of the nominal mission at 9.86. We're going to encounter Venus again in about a year's time, a little over a year's time. Okay, so that's where we are. We've had our last encounter was encounter 17 at 11.42 solar radii from the sun. Okay, now Parker Solar Probe is an interesting mission because it goes so close to the sun. We're used to seeing the sun rotate in front of us because we're so far away that solar rotation 26 days is faster than our orbit. But as Parker moves in, it actually goes retrograde. So when it's far away, the sun rotates faster, so it appears retrograde on the surface of the sun. But then when it comes into perihelion, it rotates faster than the sun. And so this is the drawing of the projection of the Parker Solar Probe orbit on the surface of the sun. So you can see that there are 2 periods where it crosses co-rotation. And when that happens, the probe is moving really quickly radially. So it actually sometimes observes the solar wind coming from the same source on the sun while it moves rapidly inward. This happens twice, once going in and once going out, with a major difference that when it's going in, aberration adds. The solar wind's coming at you, so the effective speed of the spacecraft, which can reach at perihelion above 150 kilometers per second, is the fastest spacecraft ever made. Not thanks to us, thanks to sun's gravity, of course. But as a result of that, the mission looks different going in and coming out. Not only that, you can happen to cross the same solar wind twice and actually measure the acceleration of the solar wind by one spacecraft. So now these are the first data that ever came down from Parker Solar Probe. The first quick look data that we got. This was just a few weeks after the mission started, after the first period heating, the first encounter. This is a measurement of the radial component of the magnetic field measured in nanotesla. So it's measuring the magnetic field. We're clearly in negative magnetic field polarity region, but the magnetic field is going whoop, whoop, whoop on time scale of just seconds. And you can see the envelope. So what's going on? Are we so close to the heliospheric current sheet that we're continuously crossing above and below, above and below, above and below, but like many hundreds of times per second? Is that what's going on? Well, no, that's not what's going on. What happens is we are measuring a turbulent flow and the turbulent field, which is so turbulent that the field lines actually twist back like mavericks on the ocean. Their amplitude is so high that it twists the magnetic field back into an S shape. And we call these things switchbacks. So this is the first major Parker observation. And it's really interesting because you see these switchbacks actually come in what we call patches. You see there's like a group of them, then another group, then another group, then another group, then another group. And they invert the radial magnetic field. So from negative, it becomes positive. But if you look at the magnitude, overall magnitude of the field, which is the black line here, and this is an inset, which is showing a half hour, 2 hours here, actually, this 15-minute resolution are the tick marks. See, the magnitude of the field is basically constant. So the magnetic field is oscillating widely, but the magnitude of the field is the same, which means that the field is actually, the tip of the magnetic field vector is actually moving on the surface of the sphere. This is a very strange set of affairs. It's a very peculiar regime of turbulence, and it's characteristic of a typical wave that occurs in plasma, which is the large amplitude alpha wave. In correspondence to these switchbacks, we observed that the solar wind speed had jets, positive jets occurring all the time. And these jets also are characteristic of waves coming away from the sun. So probe showed that most of the time, even in very slow solar wind, there are these humongous waves propagating away from the sun. Waves that you wouldn't imagine when you saw those pictures of the solar corona and the structure. It looks, steady and tranquil. It doesn't look turbulent. But now instead of imagining the corona as a kind of a flat ocean, you've got to imagine it as being the Pacific during a really bad storm. It's continuously, this high-speed solar wind is continuously, all solar wind is continuously dominated by this very jetty and turbulent magnetic field structure. This is the same thing seen in Encounter 9, where we're now getting much closer to the sun. This is the radial component of the magnetic field. Now you see these oscillations, these switchbacks are much smaller amplitude. And that's because we're closer to the sun. So one of the features of waves propagating away from the sun is that they become larger and larger and larger as you move away from the sun. And the reason is that the average density of the solar wind is becoming smaller and smaller because of spherical expansion. And that leads to an increase in the amplitude. So in the first orbit at 35 solar radii, we saw these huge waves. They become slightly smaller, but their nature is pretty much the same. You'll notice that these are the sort of, you still invert the polarity. The magnetic field far away is like minus maybe 20 nanotesla. Then it becomes positive, negative, positive, positive. And then here we have the crossing of the heliospheric current sheet. That sheet that I showed you, that warped sheet. And so the magnetic field changes sign, but then you see the switchbacks going the other way. Okay. And then you see them and you cross the heliospheric current sheet again and so on. Encounter 12, pretty much the same. This is the radial magnetic field. The intensity of the field, the average field becomes bigger when you get closer to the sun. You have these patches on them. And then here's the heliospheric current sheet. And then you come across and on the other side. Now, it's not really important, but this is to show you that there's a correlation between the velocity and the magnetic field, and that these are actually waves propagating away from the sun. These are turbulent waves propagating away from the sun. It's as though you were on a shore and the storm is far away and you're seeing the humongous waves coming at you, the mavericks coming at you at the beach, coming towards you. They're always propagating in your direction. You don't see any propagating from the beach away towards the ocean. And they have a spectrum, which has a well-defined power law. Now, what process generates these things? Well, one of the processes that generates them is the fact that magnetic fields are stretched out by the solar wind, and they become like elastic bands, and they can break. They can reconnect when they come close to magnetic fields with opposite polarity and lead to then, like a broken elastic band, a large like whiplash coming back towards you. And that's one of the thoughts that we have on the sources of this. Although we believe that it's probably not the main, we think this is a process which just generates the waves that come away from the sun, but it's not directly the source of the inversion of the magnetic field and the formation of the S shape. So this is an example. This should be a movie. I hope this plays. This one plays. And in fact, if you look carefully here, if I'm not mistaken, you should, oh, here it is. Here it is right here. You see an eruption. You see with that kind of slingshot effect that I was telling you about. So even in the coronal hole, which is basically unipolar, you still have small arches on small scales that actually invert and produce these things. This is a movie, by the way, from the Solar Orbiter mission. So I'm going to skip all this blah blah about the origins and dynamics of this. That's very interesting. But Solar Probe, for the first time, manages, when it sees those patches, it looks like these patches correspond to what's called supergranulation on the sun. Their size corresponds to that. So I should have mentioned that when we're really far away from the sun, we can't really see any trace of the origins at the sun. But with Parker, we're seeing all this structure, which is an imprint of the magnetic field. The magnetic field, on the one hand, has this dual behavior. The magnetic field is what constrains the hot corona, but it also generates the hot corona. So it's a cage, but it's a dynamic cage on the sun. So we now think that this process called magnetic reconnection is also at the source of coronal heating and the formation of the solar wind. And here I'm showing you the speed of the solar wind. This is encounter 10. We see these patches of switchbacks and we see these jets of radial flow. And now we measure energetic particles in the same location. And so we can see that this process in the lower corona is probably what energizes the solar wind. And it's connected with structure at supergranulation scale on the sun. I'm not going to go into detail. I don't have really time. We can measure, as I said, if you now properly plot, because the spacecraft has this kind of retrograde motion, you can plot the measured solar wind speed as a function of longitude and latitude in the solar frame. And so you can kind of line things up and notice that it crosses the same stream more than once. And if you do that, you can try to measure the acceleration of the solar wind. And you can see that the solar wind seen by probe is still accelerating as it moves further away from the sun. So the wind is observed by Parker is usually very slow, and it's still accelerating. These are all the solar wind measurements as a function of distance. And when you put them all on a plot, the original theory of Gene Parker of a thermal solar wind sits at the minimum. But in fact, the solar wind is always above that value. And so what that means is there's a role played by dynamic events. Dynamic events that probably are the source of coronal heating and these whiplash waves and turbulence that accelerate the wind itself. This is too complicated. Solar Probe now actually measures the fact in situ that the electrons in the coronal hole are colder than they are in the active sun. And this is kind of the plot that shows the electron temperature as a function of speed at different distances from the sun. And when you're far away from the sun, the electron temperature is all over the place. But when you get really close to the sun, you see that the slow wind has hottest electrons, a black line, and the fastest wind has the coldest electrons. This process of magnetic reconnection occurs, and it's pretty dramatic. I was talking about the magnetic cage. Parker Solar Probe initially observed very slow solar wind. And one of the reasons for that is that the actual magnetic shape of the field that opens up into the heliosphere can be very, very, very peculiar. We tend to think of the magnetic field on the sun as being uniform, but it's not. It's concentrated in nodules. And so you can have a very small region on the sun that opens up and occupies a very large piece of the heliosphere. These are so-called coronal funnels. And those tend to create very slow solar wind with a lot of turbulence propagating outwards. And we think that's what Parker was seeing at the beginning in its measurements of the heliosphere. This is another beautiful example of a piece of heliosphere created by a very small magnetic imprint on the sun. And here I'm trying to show this. This is a Proba 2, an instrument in space around the Earth. And you can kind of see that there are regions that funnel out dramatically. Hopefully you can kind of visualize that here. And this is the same kind of idea as seen by now solar orbiter that carries telescopes to the orbit of Venus. So here you're not seeing a zoom created by a zoom on a telescope. You're seeing a zoom due to the orbit, spacecraft coming closer to the sun. And you can see now some of the expansion of the wind directly. And you can see the activity associated with sunspots and active regions on the sun. So why is fast wind fast and slow wind slow? So we think that the fast wind comes from these coronal holes. The slow wind is the one that's magnetically confined by the solar corona before streaming out. In addition, the magnetic field mapping from the sun into the heliosphere becomes very singular, some regions which at the boundary of closed and enclosed fields. And so these regions here tend to produce very slow wind as well. Let's show you some things from the in situ measurements. So this is the telescope on Solar Probe. And this is one of the first images where it caught not only the galaxy, as you can see here. These are two cameras. And the reason there are two telescopes is that the antennas can diffract light and reflect light into the spacecraft telescope. So to avoid the light coming from the reflection by the antenna, the decision was made to make two telescopes that don't quite, they overlap a little bit, but they try to avoid the scattering of light from the antennas. So this is the inner and this is the outer, and these are the rays from the sun, but we can see the whole, basically the whole solar system from a very strange point of view, because you see now Mercury here is the furthest away and Mars is seen as the closest planet, and we have Venus and Earth. So let me now show you when whispers, when we're moving along, what we are seeing now is the fact that the heliospheric current sheet, which should be located there, is very dynamic and erupts in a series of blobs generated by this process of magnetic reconnection. This is a fundamental process in the laboratory. And it's one of the reasons that we don't have confinement and we don't have nuclear fusion, because currents in the plasma tend to collapse and create these blobs that lose confinement. And that's basically what the solar wind does as well. And so this is these are really dramatic images that show how the heliospheric current sheet is active and creates blobs. These blobs, when they get to Earth, by the way, they push the magnetosphere and create substorms and storms. So this is a really impressive movie from the WISPER telescope. These are more of these coming from, and you'll notice that WISPER also observes when dust hits the spacecraft, it creates these streaks of lights from ionization by hitting the spacecraft. So you see some noise as well and you see these lights that look like kind of comet, these kind of look like meteors, but they're really just the path of dust. Parker has shown that the dust kind of disappears inside 15 solar radii, as had been thought before, because radiation pressure becomes so strong and heating becomes so strong that it sublimates. So there's a dust-free region really close to the sun. This is another image of the dynamic current sheet and the kind of the pulsating magnetic reactive eruptions that occur there. Okay. The theory of that magnetic reconnection is something that we've been working on very, very strongly. And you know, this is basically, these are magnetic field lines, and this is a sheet of current that collapses on itself. As it does, and you go and look at an inset, you get another sheet that collapses again, and basically this process is self-regulates, and it leads to very, very quick timescales, even though the gas is very conductive, and so something which was not appreciated at the time. And it happens in the heliosphere, in this forming heliospheric current sheet, and we now have models of this that we are testing with Parker Solar Probe. Now, another interesting thing that Parker has shown is that as the sun goes from solar minimum to solar maximum, the number of current sheets that I showed you the simple case of a dipole with a tilted current sheet. But as we go to more and more active sun, the dominant polarity of the corona is no longer a dipole, but it can become a quadrupole or an octopole. And therefore, that means that you'll have multiple current sheets, which have very, very strong effects on space weather. So I hope I've given you at least a hint as to some of the interesting observations made by Parker Solar Probe. And I'd like to conclude by saying that Parker establishes conclusively that nonlinear plasma and magnetic field dynamics at the solar wind source and the coronal imprint play a major role in determining the structure of the solar wind and the dynamics that occurs later in the heliosphere. There are still some questions. Where do we form switchbacks and how? And we need joint observations by Parker and Solar Orbiter and other telescopes to do that. What is the role of reconnection and alpha waves, these large amplitude turbulence that I told you about, mavericks? And there's all the kinetic physics associated that I didn't go into because it's a little bit more complicated, understanding why you have density fluctuations and what determines what the particle accelerations profile looks like, which is kind of complicated to do. But, you know, we're midway through Parker. Solar Orbiters has a few years to go. Solar Orbiter is going to move up. It's going to use Venus to deflect out of the ecliptic and to observe the magnetic fields closer to the poles. It's very hard to see the magnetic fields at the poles of the sun from the Earth, because the way we measure the Zeeman effect, we see the line of sight magnetic field. And so if there's a magnetic field coming straight out of the pole, we don't measure it. And so we have only brief and intermittent measurements of the polar fields, because using the 7-degree inclination of the sun's rotation axis. But to understand the dynamo, we really need to go up there and see what the flows in the magnetic fields look like. So in the future, I think we really need basically 3D studies of the heliosphere. We're now a spacefaring society. We have spacecraft going throughout the whole solar system. If you want to predict the explosions that occur, coronal mass ejections, solar flares, and magnetic reconnection, you need to see the full magnetic field in 3D. So we need satellites that will give us better coverage than just the Earth point of view. Of course, probe and orbiter are single satellites, but ideally we should have constellations of satellites going above the ecliptic, going around the sun to give us multiple points of view. It's the only way they're going to really nail down coronal heating and the stability of the solar corona, understand why the sun is magnetic, the solar dynamo, and understand the process of coronal heating. All right, I'll stop there. Thank you very much. I hope that's okay. Hello. I put you all to sleep, maybe.
Check 1, 2.
Oh, we're.
I just don't know how to unmute my microphone, that's all.
Yeah, class.
Technology is not my strong point.
All right.
So let me first tell Spencer, if you're listening, we are in fact going to try to give away some door prizes in here. So can you do something to make sure that people online also have an opportunity to do that? And do we have any questions in here? Question. Okay.
Thanks, Marco, for excellent talk. My question has to do with something you mentioned in the beginning. You said that protons stay in the sun because they're too heavy and electrons fly out. Can you explain again how come the sun does not get charged in that process?
Well, the reason is that, basically the electric field, if the electrons were actually did leave and left the protons behind, the sun would very quickly become charged. And the forces, remember, we humans are kept together by electromagnetic forces, but not by the bare electromagnetic forces. We're kept together by the residual electromagnetic force that comes from the fact that the protons and the electrons and the single atoms and molecules don't neutralize each other perfectly. So imagine bare protons and electrons. You'd very quickly get a huge electric field. They would drag the electrons straight back to the sun. So what happens is that the electrons try to escape, but they can't charge the sun, because the minute you had bare charge on the sun, any significant bare charge on the sun, the forces would become so huge that they would completely dominate over any kind of gravitational force. And so basically what happens is the sun remains neutral, and the electrons and the protons flow out together, maintaining neutrality, essentially maintaining the sun neutral. But the fact that the electrons are so light means that the protons are forced to follow this electric field, we call this a polarization electric field, which exists as a result of the fact that everything is outflowing. And so the scale height of electrons and protons is different. And so that sets up an electric field, which does not charge the sun, but it results in sort of the solar wind. But it begs the question of, why are the electrons so hot? And that has to do with the magnetic field. And this simple image that I told you does not take into account the fact that there are arches and closed magnetic fields on the sun. So everything's a little bit more complicated than what I said. But that was just to give you a feel of why, if you had a very hot corona, you would imagine it to expand.
Okay, we have one more question in here.
Hi, Marco. That was wonderful. My name's Victoria. The end videos you posted were quite lovely. My question is, let me see. I wrote it down so I wouldn't forget. So can we assume that this data is applied to other suns and stars elsewhere? And how does the mass actually change, like the mass of a different star or sun, change the data?
That's an excellent question. So what do we know about magnetism on other stars? Well, all solar type stars and later, G, K, M, etc., display magnetic. In fact, they display increasing magnetic activity because typically the smaller stars, K, M, etc., they tend to rotate faster than the sun, so they have stronger dynamos, stronger magnetic field, stronger magnetic activity. They have huge. I didn't show you prominences, and I didn't discuss solar flares here. But M dwarfs tend to have huge, humongous prominences, huge star spots, sometimes spots that seem to cover, like 30 or 40% of the disk of the star. And these are measured indirectly. And so we're only beginning the study of comparative sort of astroactivity. But we are doing that now. And so people are studying, for example, the effect on exoplanets of magnetic fields. And so that's a very open and active range of study. I don't have answers for you because we don't have many answers for the Earth either. So it's really we know what happens, but we have hard time predicting the solar activity cycle. It's really funny. We're really lacking basic measurements. All of the solar dynamo theory that exists is based on trying to reproduce the 11-year solar cycle, and so there are a lot of tweaks in the theory. 3 parameters that are adjusted to make the cycle last 11 years, or the half cycle. The full cycle actually lasts 22 years. And so in order to see if the data support these models that we have, we need to measure the flow and the magnetic fields towards the polar regions of the sun, which we haven't done yet. Now, if we had telescopes that could measure and resolve the disks of other stars and could give us measurements of the flows and things, that might work. But for the moment, we have to do the opposite. When we look at a star, we have to try to think of our sun, downgrade our resolution to 0, and say, what would we see if we were observing just the sun as a point source? And how could we use what we know of the sun and its 11-year cycle to determine what's going on other stars? And so numerical simulation and this kind of work is what's being done. So unfortunately, I don't have big answers to you, but people that study this are, of course, interested in the effects on life. Life exists on Earth probably both because of solar activity and thanks to the Earth's magnetic field that protects us from solar activity. And so, of course, if you create a star that has much stronger flares and weaker magnetic fields, well, then the radiation, the high energy particles that impact on the planet are probably too much to allow for carbon-based human type life to develop. While on the other hand, you might have a much more active star, but you might have a much stronger field in the planet that protects it. And so, all these things are, you made a very an important question for now. This is what we're trying to do, and it's the future of our field, essentially, of understanding the sun in the context of other stars.
Are there any questions from our Zoom people? I hear nothing. Are there more questions in here? Oh, way back there. Get your exercise in.
Good for me.
If there are questions from the Zoom crowd, type them into chat and somebody up in the control booth will tell me about them.
Hi, Marco. My name is Justin. Thank you for the awesome presentation. You had mentioned that a mission like the Parker Solar Probe was conceived a while back, and I'm curious how much in the time it took from conceiving the idea for the mission to actual launch, I guess, how much of a hurdle was it developing the technology to deal with the heat of the sun on the spacecraft and also keeping it cool enough to operate?
Right. So basically, as you can imagine, that was one of the main issues. Well, two or three issues. One was the design of the original mission, which, the price was too expensive for the mission data that was coming down, essentially 1.5 billion, $1.5 billion for 16 hours of data was, even for the 60s NASA was impossible. But then, of course, there were technological hurdles. People thought they could create a thermal shield, but but in fact, the thermal shields were developed, and as you can imagine, it's essentially a piece of, it's a ceramically coated carbon foam, which is essentially around 3 meters in diameter and 10 centimeters thick. And it's proprietary. It was developed at Johns Hopkins lab. And as you can imagine, the defense is involved. So we don't even have access to the detailed structure of that. As far as the radiator is concerned, it's much easier. The radiator is water. It's like an old car. It's essentially a water-based radiator, because if dust, we were worried that if dust pierced a hole in the radiator, then if we had a complicated molecule that started getting ionized, we wouldn't understand anything of what we observed with our particle detectors. But water is basically hydrogen and oxygen, so we would have had a good handle of what was coming from, a loss of water on the spacecraft and what was the solar wind. So that was the reason behind that. But the shield is a miracle of technology, and you can go on Johns Hopkins website for Park Solar Probe, and you'll see a lot of details. I didn't show you movies of the building of the shield and the putting in place. As an additional piece of information for the technology of the mission, the engineers develop a mission. All they care about is getting to the place where you told them to. They don't care about the solar scientific measurements really that much. So what happened in the initial thing, of course, if you put all the instruments and the whole spacecraft behind the shield, some of you that are into this maybe more than others will realize that the forces, gravity acts on the center of mass that attracts the spacecraft to the sun. But the light that reflects off the shield exerts pressure at the front of the spacecraft. That means that you have an unstable situation, right? Because the light is pushing at the front, but gravity is attracting essentially from the back. So all you need is a slight misalignment of the center of gravity with the center of the shield, and there's going to be a torque. And that torque will act to twist the spacecraft around, pushing the shield in the back and attracting the center of mass to the front. So we need to realign the spacecraft dynamically, essentially quasi-continuously. And the way the engineers envisioned to do that was to use engines. They were firing every minute or so. But if you fire them every minute, when the engines fire, we can't make measurements because they pollute the solar wind. So we had to require the spacecraft to have momentum wheels so that the way in which you do it is actually passive. We adjust the center of mass continuously to rebalance the spacecraft until these wheels reach the end of the shafts on which they are. Then only once every 20 minutes or so, when we're at perihelion, a half an hour, do we fire the engines to rebring the masses to their origin and allow the system to work again. Now, the other question you might have is, was the mission still worth doing 70 years later, right, from when it was originally thought? Well, there's one experiment that we didn't do, which was originally planned, which was the general relativity experiment. We have now, we've measured gravitational waves. We have spacecraft around the Earth that use general relativity to actually measure the details of the distribution of mass on the Earth to a higher precision than ever, so that a gravitational measurement at 12 solar radii was no longer of relevance to the mission. But everything else, understanding coronal heating, understanding the source regions of the wind, understanding how the magnetic field acts to generate the current sheet and what the sources of the solar wind are, and then the acceleration of energetic particles, remain as much a mystery today as they were 50, 60, 70, it's almost 70 years ago. So we really badly needed these measurements to constrain theories and models.
And I will add the comment that while you might not have thought about spacecraft, is also a problem for the James Webb Space Telescope. And
Right.
So they have to fire their jets because of light pressure on the very large solar shield. So the sun's a pain in the neck no matter where you go.
It's also why we're here, though. So
Yeah. So there was a question from David Velarde on Zoom. saying, is there a mission to have a network of such probes to measure the same solar events from multiple probes simultaneously in support of your 3D studies?
So as you know, that we have decadal surveys in all of these fields. And so in heliophysics, the decadal is ongoing right now. And I think that in the decadal, what we'll find is that there are probably two missions that are going to be up at the top from the heliophysics point of view. I'm not talking about magnetospheric or planetary space weather, but from the point of view of general heliophysics, I think the two that are going to end up close to the top there are going to be an interstellar probe trying to understand really what's going on in the environment of the sun in the interstellar medium, and a multi-constellation spacecraft trying to observe the heliosphere in 3D by sending some polar spacecraft and some spacecrafts at large longitudes away from the Earth. Lagrange points perhaps included. Yes, I do think that's going to happen in the coming decade or two. I mean, if you think of it, we cannot send astronauts to Mars. I mean, I don't care what Elon Musk says, but we are not capable right now of sending astronauts to Mars that will survive. So in order to have them survive, we need to do two things. One is to be able to predict with sufficient advance warning, and then to have a safe hiding place for astronauts during the travels, and then to create something on Mars that will protect them from large solar events.
And there was another question about the fuel. How much fuel is being used when you fire your jets? So how much time is left in the lifetime of the spacecraft?
Right. Yeah. So the fuel is used essentially only very close to perihelion. When you're far away, this problem of instability is not that bad. Together with the momentum wheels, we only fire every few hours. And so the prediction that we've made was for the spacecraft to last until the late 2020s, 2028 or so. Once we exhaust all the hydrazine, what's going to happen is that slowly or surely, but the momentals really going to reach their extent. The spacecraft is going to flip, and the instruments are going to melt, and we're probably going to create a small dust cloud around the sun slowly with the carbon shield. Given what we've used so far, we now think that we're in the clear until the mid 30s. So the spacecraft can actually last a lot longer than we predicted.
So will we be able to detect its demise from here in the solar wind?
Who knows? That's a good question. I haven't really thought about it. But that'd be kind of late. It's going to take a while for that to happen. I imagine it would take at least a couple of years after the end of the mission. So if the mission ends maybe in the late 2020s, then perhaps, with telescopes, we should be able to see something. I should have showed you, we do have one solar probe that has flown in the past, which was Comet Lovejoy. I don't know if you've seen the movies of the comet going through the solar corona.
Not that one, but I've seen movies of sun-grazing comets that come in and don't come out.
Right. Well, that was spectacular because it came in and actually managed to come out as well. So, anyhow, I should have put that at the end of this talk.
Are there any other questions in here? No other questions in here. There's one more from Zoom. What general relativity data related to the mission before the objective was abandoned? From Alicia.
Well, the idea was to use, you wanted to measure the acceleration, right? So a spacecraft going at 4 solar radii would have been able, by time, you would have been able to see the effect of gravitational retardation of the signals coming from the satellite to the Earth. So we would have had detailed measurements of the sun's gravitational field. And with that, we could have had tests of general relativity, the refraction of light by gravity, essentially, was the idea. And precession of clocks. Clock in the very intense gravitational field of the sun will run slower. So the clock of the spacecraft, when it came back from the orbit, should have been running slow compared to what the same clock that we had running on the Earth, right? So
right.
Measurement of how much slower it was going would have given us the exact replica of the twins experiment, the general thought experiments of the twins in space. Yeah.
So did they ever get a chance to actually make research papers out of that, or was it just completely abandoned and no data was gathered?
Well, no, we don't have the experiment. We don't have,
Okay.
we didn't create what was necessary to do that experiment with the probe.
Okay.
Yeah.
Okay.
Okay, so is there any more questions in here? Still no questions in here. Any more questions from Zoom?
All right, so I've just posted the link for the drawing on Zoom, on the chat for the Zoom people. So we've only had about a handful of people sign up, so
So I figure we give away, because of the low turnout, maybe 3 door prizes inside and 3 door prizes to Zoom. And Alicia, since you are here, what do you think we should give away?
Well, first question is, are there any lasers there or not? I don't know if they made them there.
Um, Dar-
If not, I have other things.
Daryl has the lasers and nobody picked them up from his house. Yes, we were going to enslave the indoor crowd by giving them all lasers, whether they wanted to or not. We can still do that or
I can give it up.
charge and do
It's okay.
something.
Okay. All right, let's do this.
all right. So I'm going to close out the drawing for the Zoom folks in about a minute. So let me repost the link one more time, and please.
Okay.
While we're doing that, I do have one speculative question, which is, once you guys learn everything that you need to know about our star sun, do you think that will apply to all the other suns and stars in the universe?
Well, I think to the extent that that the physics is the same, we believe they will understand. I mean, no two stars are exactly the same, right? The rotation rate might be slightly different. The inclination of the axis with respect to the, so even if you look at a sun with the exact same composition of the sun, the exact same mass, the exact same age, if for some reason it has a different rotation rate, or it's in the neighborhood and it interacts differently with the interstellar medium, it has a different set of planets around it, its history might be different, and its magnetic history might consequently be different. It might have a convection zone, but if its differential rotation inside is a little bit different, the way the cloud collapsed is different. So the solar rotation profile inside the star was different. That would create a different dynamo. So I don't think, there's two stars that are exactly identical, but the physics we think is the same. Once we learn the main way in which the sun makes its dynamo, we'll be able to predict how other stars might make their dynamo as well.
Thank you.
So it's yes and no, as usual with physics, right? You can predict certain things once you've learned something.
We need to call numbers over here when you're ready, Tim.
Yeah.
Okay. So shall I say bye?
Well, you can. Are you for the online door prizes?
Hang on just a second. I'm collecting them now. So I just closed out the.
Okay.
So give me about a minute, and I'll get those out for you.
Okay. So when we do the door side, we're going to need to know who you are and what your email address is. So when we pick you, because some random soul is going to win something, come down here and give him your.
I'm leaving. Actually, we'll have you write it over here. We can tell Alicia; she'll figure it out on her end as well.
Yeah.
She'll get it. Once Alicia has it, we'll be fine.
Okay, I'm ready for the drawing online. You want me to do this one first?
Go right
Yeah, let's do something for the Zoomies first.
Okay, hang on a second.
Okay, there I am. Now you can see me.
Okay, now, okay, all right. Okay, I'm sharing the drawing for the All right. Okay, so Robert Farley is the first winner.
Woohoo.
Okay.
What did I win?
Robert Farley won some Constellation drinking glasses. They're really nice.
Great.
Oh boy. Let's do one from in here. And what I'm going to do is pick a random number because you all got number tickets. And the random number is 30. Oh boy. Okay. Random number 30 is a winner.
Yeah, if you would come on down and we can just write your name down or tell us, so we can tell Alicia who you are, and she'll be able to get it from her end real quick, much faster that way.
What do you-
Is it best if we just tell you his name and his email, or
No,
No, we don't do that.
Yeah, you
right,
can send it to
write them
me.
down.
huh?
Write them down.
Write 'em
Yeah,
down.
He won
and
an
we'll
item. Yeah. He won an item from the LAS store.
Okay.
Let's hear some applause. Hooray! Somebody wants something. Woohoo. Wake
Boy,
up, everybody.
What a bunch of deadbeats in
Yeah,
here.
my God, congratulations.
Okay.
It was
Yeah.
a really good talk. I was.
Yeah, it was. Yeah, he was
I
great.
studied this stuff in college, and I was just like, "Oh my gosh, that's so
Yeah,
Oh,
it's
boy.
amazing that he knows.
Okay, pick some.
All right, hang on. Christina Valari.
Yay. Applause. Round of applause.
What did she win?
Christina Velarde won an observer's map of the moon.
Oh boy. There was a question, somebody asked, where's the LAAS store? Where do you go to get at it? The LAAS store is not a store. It's actually on the
It's
web
online.
page. It's online. You can get at it through the web page, and basically when you win something from the LAAS store, you buy something, and then the LAAS pays for it. So let's do from in here. 14. Oh, 14.
Give him a round of applause. Come on, guys. Yeah, wake up here. There you go.
What is
What was the question? You cut out. Oh.
What
Give
did
Tim
number
the
14
microphone,
win?
I
What did
agree.
he win?
what was that?
He won a eclipse book called America's First Great Eclipse: How Scientists, Tourists, and the Rocky Mountain Eclipse of 1878 Changed Astronomy Forever by C.
Oh
Preston.
boy. Just write
It's a
down your
really
name,
good book.
email address.
Mhm.
So he won the eclipse book.
Mhm.
Oh
In
boy.
honor of the eclipse. And
I
the
hope you
upcoming
like
one.
eclipse books.
Yeah, we just made our reservations to go see it.
Oh, okay.
So timely.
Hey, there you go.
Okay, one more for online.
Yeah, go
Yeah.
right. Yeah, go ahead.
Okay.
Shane Winter.
Oh, you can just leave it there for now. Yeah, just make sure your name and emails on it that's legible.
Thank you.
Yeah.
And if they're not legible, I'm going to have Tim take care of that.
Okay. Shay Winter won a LAS 11-ounce mug from our store.
Yay.
Oh boy. And one more from inside.
Yep.
I picked the one that's already been won. How about number 8?
Who's number 8? Congratulations. Yay. Come on, round of applause.
Oh boy.
And what does number 8 win? Alicia?
And number 8 won a red flashlight used for nighttime
red-
viewing.
All right, red flashlight.
Oh, boy.
love those.
I hope flashlight, to your name and your email address.
Congratulations.
And then Alicia, you're giving us your email address because Alicia will send you an email and ask you for a mailing address to which to send the gift you won, if it's something we can send you.
Okay, here's the last one.
That's 3, number
Are
3,
we doing
right?
another one?
Is that only 3?
We did
Right,
3.
Spencer, only 3?
Yeah,
We
this is third one, right?
Yeah.
No, we did 6. We have 6.
So this is Soren Fay.
Oh, we're doing another one?
Oh, I'm sorry. Oh, we've already done them. I'm sorry. Sorry about that.
We've done 6.
Okay.
We completed all
All right.
Spencer. We're done.
All right. Okay. Done.
Okay. So there you are. On the door prizes. We're finished with the talk.
Get on camera there. There you go. Thank you. Hey.
There you are.
You're cutting out, Tim.
Where? So it's time to say goodnight. Thank you for coming to the meeting. Come again. It'll be very exciting.
Yeah, and don't forget, October 28th, 3 o'clock at the Garvey Ranch for the science fair. Bring a costume if you want. And it's going to be a lot of fun.
Bring a copy. Not.
Okay. That's it, I think, right?
Good night.
Sir? I think that's it. Okay. Good night, everybody.